Hello guys, in this video I'm going to show you how to solve count of structurally unique binary search trees. So given a number n, write function to return the count of structurally unique binary search trees that store values from 1 to n. So as you can see, this one is pretty similar with the previous problem, which is unique binary search tree, right? uh, but this one is even simpler because we just need to count how many binary searches instead of finding all the binary searches. All right, so let's walk through an example. So for example, n equal to 5 to 3, for example. Okay, so what are the unique, structurally unique binary search trees? So because n equal to 3, so all the nodes. So for in one specific tree, it must contain all the nodes from 1 to 3, right? So in order to find or to count all the unique binary search trees from this number, we could uh, we could consider each number here is a root node, right? Then want to expand on that. For example, the first root node could be 1, and the second root node, let's say 1 first, right? So if we decide to take 1 as a root node, then the left of 1, uh, the left child, the left side 1 will be everything that is on the left of 1, which in this case we have nothing. So the left child of 1 in this case would be no, and the right side will be let's make it general here. We must somehow put we have 2 nodes left, which is 2 and 3. We must somehow put 2 and 3 on the right side of this of node 1 here, and as you can see, this here again, the this is actually a sub-problem of our original problem. So our original problem is from 1 to 3, how many structurally unique binary searches we can find. But here, if we consider only the right subtree with node 2 and node 3, so our problem will be given the input 2 and 3, how many uh, structurally unique binary searches we can find, right? So this can be further Okay, let's say um, if we find if we succeed to count the number of structurally unique binary trees on the right, let's say it would be x. Uh, let's say we can find x binary trees on the right, and here on the left it's a no, so it's obvious that there's only one possible case for the left subtree. So it means the total of nodes, the total of binary search trees we can find if we take node 1 as a root would be x multiplied by 1, right? Okay, here is a formula I'm gonna use. Okay, but let's continue with this with rise of trees to find what is the x here. So again, our problem here is the same as the original problem. It's just a sub-problem of original problem. So here we have two choices, right? Again, we have two choices because we have two nodes. So we have two choices. First is to take 2 as the root node here, and the second choice is take 3 as the root node. Okay, so if I decide to take 2, let's copy it over here. If I decide to take 2 as a root node, right, then what I mean is then the left of node 2 here is everything that is on the left of 2, which is in this case nothing, because we only consider 2 and 3 here. So it will be no. And on the right side of 2, we have one value to be put here. So it would be 3. So obviously here on the left side is no, on the right side is 3. So in this case, on the left side we have one choice, on the right side we have one choice. It means if we consider 2 as a root node of this right subtree, then we can only build one structurally unique binary search tree, right? So let's go. So we're done with this. Here is a complete structurally unique binary search trees contain all values from 1 to 3. But here we done with 2, right? We move to 3 and we proceed with 3 here and take it as a root node of this right subtree. Okay, if I take 3 as a root node, what does it mean? So the left of 3 would be every values on the left of 3. In this case is 2, we have one value. And the right of 3 here would be any values, could be taken from any values on the right of 3. In this case we have nothing on the right of 3, so it would be no. And here in the left side we have one choice, on the right side we have one choice. So it means if we decide to take 3 here as a root node, then I can build another structurally binary search trees combine these two cases, it means that from these two values we can find two structurally binary searches, right? So from the left we have no here, which means one possible uh, one possible count, and on the right here we have we can build two structurally binary searches. So apply this formula: 1 times 2 is 2. So again, uh, so it means if I take 1 as a root node here, I can build two binary searches, right? So we just repeat that process in order to find the result, right? We take every value as a root node, right? One by one. Here we're done with 1 and we want to proceed with 2 and 3. Then we're going to combine the result together. So it's enough for explanations. Let's get into coding. Alright, so from num here, I think I'm gonna use a loop, right? We need to iterate through every number from 1 to n and consider that as a root node, right? So for that, let's say val root val is from 1, start from 1, go all the way to num, then root val plus plus. Alright, so for each root val here I will take the root val as the root node, right? Take values from root val value on the left side of root val as a left subtree. Same here. Take value on the right side of root val as a right subtree. Right. Then here I want to combine. So because here we only need to count the number structurally unique binary search. So probably you don't need to store anything for this step here, but you take value from the left side of the root val. So it means the left side root val will be from 1 to root val minus 1, and I need to call this one recursively, call this function recursively, and we need to pass these two values down. So because our function signatures now is only num here, so one way is to define a private function inside here, and this function will take in a start and end, and here instead we wanna run from current start to root val dot minus 1. So it's the same as calling these functions recursively. Passing in start is the old start, and end is a root val minus 1. And this I I want this function to return the count, how many structurally binary searches we can find from this range. So let's say left count, and same here. Here's a right count, but I'm gonna run from the root val on the all values on the right side root val, which is root val plus 1, go all the way to the end instead, right? So combine the value, right? So if I take this as a root val, I can find left count times right count number of structurally unique binary searches, but this is only for this number as a root. We need to accumulate that, right? So initial value will be 0, and for each root here, I'm gonna add up to the output value, right? So in the end, I can return the output. So here I will call this one with the initial value count unique binary search. Be careful, this should be the private function we define here, and the start would be 1, right? We're gonna start from 1 to the end is num, and I'm gonna return this. One last thing here, these functions is recursively call, so we must have a base case, right? Base case. So what is a base case here? So our base case could be when the start equal to n, or let's say when the start greater than or equal to n. So let's say in this case here, if we take 1 as a root node, right? So on our left side will be from 1 to 0, right? So it is start greater than n. It start greater than n. So it means that we only have one choice here, which is no, right? No on the left side. And if, for example, we have node 2 here, and on the left side will be from, if we take 2 as a root node, left side will from start is 1 and end is 1. So start equal to n, we have only one, we can build only one structurally binary search trees, right? So return, this guy is 1, right? So return 1 here. Alright, I think that is it for this one. Whoops. One last thing. Here, because we try to parameterize it here from start to end, and we call it recursively, so the root val here is no longer from 1 to num, but from start to end. Be careful with this. Okay, it works. So that is it for count of structurally unique binary subtrees. And thanks for watching. See you in the next video.